Good morning, everyone. My name is Boz Marshy. Welcome to Mallett Technologies webinar series. I've got everyone on mute for now, and we will take time at the end for questions. Again, thanks for taking the time out of your day to join us. I'm the account manager for Mallett Technology for North and South Carolina, Virginia, and Maryland. Today's topic is fracture mechanics capability in ANSYS 19.2, and our presenter today is Dr. Metin Ozen. Metin has been in the field of applied mechanics and FEA for over 30 years. I am at our headquarters, which is in Durham, North Carolina. Our website is www.mallett.com, and you can get a hold of us at info@mallett.com. Today's agenda, I'll do a quick overview of Mallett Technology. Also do then we'll have Dr. Ozen give us the webinar on fracture mechanics. And then, like I said previously, at the end of the webinar, we'll have time for discussion and questions. And also, if any questions come up during the webinar, you can type them in at the chat area of the GoToMeeting control panel. Also, this is being recorded, so if you'd like a recording of this webinar, you can just send me an email and I'll be happy to send you a recording of today's webinar. Our mission statement at Mallett Technologies is we use world-class engineering software tools combined with a broad knowledge and expertise to help our clients compete in today's marketplace to produce reliable and cost-effective products. Mallett Technology has been serving engineering customers for over 40 years. We started out as a consulting arm for Swanson Analysis Systems, which was founded by Dr. John Swanson as Swanson Engineering Services Corporation in the mid-70s. So we've been around for a long time. Like I said, we were started from as the consulting arm for Swanson Analysis Systems, and that's where the name ANSYS came from the analysis systems of Swanson Analysis. We've been a ANSYS channel partner since 1985. We were one of the first channel partners with ANSYS. Again, our web address is mallett.com. This is the first in a series of webinars we're having. We're going to have upcoming webinars. Today's webinar was on Wednesday, but our upcoming webinars are going to be on Fridays. The next one will be Friday, October 19th, and that will be challenges in explicit dynamics with FEA modeling. On October 26th, we'll do a webinar on contact nonlinearities. And on November 2nd, fatigue and weld assessment using ANSYS Workbench. We'll also have planned more, and that'll be in upcoming webinars. We'll let you know the dates, and I'll also, of course, email the dates and invitations to everyone. And like today's time, all these times will be 11 a.m. Eastern time. Again, except they'll be on Fridays instead of Wednesdays moving forward. The webinar today is on fracture mechanics, and it is an introduction to and covers some of the topics that we have on our full fracture mechanics class, which is a 2-day class. And right now we're scheduled to give a full fracture mechanics class here in our Durham office on November 8th and 9th. So if anyone is interested in that, please let me know via email or phone call if you'd be interested in attending that 2-day class here in Durham, where we're going to go more in depth on the subjects that we covered today. So with that, I am going to turn the presentation over to Metin to go ahead and start the discussion of fracture mechanics.
Hi, Buzz. Can you hear me?
Yes.
Okay. Well, good morning, everyone. So, thank you for joining us. So the fracture mechanics classes, like Buzz said, is on November 8th and 9th in our Durham office. It's really a synopsis. Right now, what we are going to go through right now is a synopsis of what's covered in the fracture mechanics class. I would like to start this by famous saying by Benjamin Franklin, in this world nothing can be said to be certain except death and taxes. We would like to propose a modification. Nothing can be said to be certain except death, taxes, and fracture. So with that, I'd like to back that up with some statistics from Battelle. According to 1983 numbers, fracture costs $119 billion a year to the U.S. economy. What is fracture mechanics? As most of you know, it's the study of flaws and cracks in materials. Mostly deals with crack growth and life estimation. And why do we study fracture mechanics? Because strength of materials approach cannot really calculate what happens to the stress state when we have a crack. So presence of cracks can significantly decrease the structural strength. And what happens is, as you know, when we apply force on a flat panel, the stress in regular strength of materials approach can be easily calculated by force divided by the cross-sectional area. But when you put a crack, right at the crack tip, the stress goes to infinity. So it's very difficult to calculate from strength of materials approach what the stress is when there's a crack in the panel or in our structures. So flow size A or crack size A is an important parameter in fracture mechanics, and fracture toughness replaces the strength of materials approach. So here we are going to talk about stress intensity factor. Right at the crack tip, like we said, as you know, the stress is infinite, but in order to be able to get a handle on the stress of the state of stress at the crack tip, we use this linear elastic fracture mechanics approach and define what's called a stress intensity factor, and that's denoted by K sub 1C. K sub 1, the 1 there, it's not an I, it's really 1, refers to mode 1, and C refers to critical. Critical being that K sub 1C it's really a material property, just like Young's modulus. And when things go plastic, then we talk about J sub 1C, and we will talk about what J sub 1C is as well. It's similar to K sub 1C. When everything is linear elastic, K sub 1C is equal to J sub 1C. But when there's a lot of plasticity ahead of the crack tip, then we need to talk about J sub 1C. And historically, as you know, there's been a lot of cases like the Aloha flight in Hawaii, German train accident in 1998, and then lately in 2014, Air Asia, which fell from cruising altitude due to just one single BGA. So here, as you see from the simulation of a BGA package where there's a bunch of different materials, when things expand and contract, there's a crack that develops in the solder joints. And unfortunately, this Air Asia crashed due to one single BGA failure, and that's what was determined. So today, instead of going through a bunch of slides, what I also prepared is a workbench file. I'll take you through a live demo, and I have two workbench files open here. One is already set up, and I'd like to show you how you would set up a fracture and how you would create a crack, and also how you would simulate the growth of that crack. I'd like to take you through that, but first I'd like to talk about a little bit of the background so that you understand how things fit in Workbench. So if we, when we have crack propagation, on the figure on the left-hand side, the y-axis is the crack length, A. So we always start out with a known crack length. And this crack length, which is the point on the y-axis here where this red curve starts, what that is really at the end of fatigue cycling, each in the parts, there's actually a crack that develops. And US Air Force standards, they say that's 10,000ths of an inch. So this A sub 0 here, that according to some standards, that's 10,000ths of an inch. So at the end of fatigue calculations, we can actually go to fracture and crack propagation calculations. So you can think of this as the end of fatigue calculations. From that point on, we can actually do the fracture mechanics calculations. So on the y-axis, we're plotting crack length, and on the x-axis, we're plotting number of cycles. So from a typical test data, this is what you would get. You would get, from a typical test data, you would get this red curve over here. Now, what we do is, in fracture mechanics, you take this curve, and you convert it to the curve that's on the right-hand side. That's a fatigue crack propagation. That's delta A divided by delta N, and that's usually on a logarithmic scale. So we take this data on the left-hand side and convert this data to this type of a plot that's on the right-hand side. So on the vertical axis, we put the A over the N, and on the horizontal axis, we put stress intensity factor range, delta K. And as you see here, the red curve on the right-hand side, it starts from a certain value. And this value is what we call the threshold stress intensity factor range. What that means is, if our stress intensity factor range is less than the threshold value here, then that means there's not going to be any crack propagation. So if our stress intensity factor range is less than this threshold value, that means we're safe. The crack is not going anywhere. But if we are above this value, meaning that if we are to the right-hand side of this point over here, then we are going to get crack propagation, and the crack will propagate along this curve here. And as you see here, there are three regions to this: region 1, region 2, region 3. What we are mostly interested in is in region 2, and this region 2 is where there's stable crack propagation. So on this slide here, we kind of talk about the initiation stage. The initiation stage can represent a large part of the lifespan. And this crack initiation stage is usually, in our calculations, we denote this as the regular fatigue life. It could be stress cycle, it could be strain cycle fatigue, but this really develops, this crack initiation stage is where regular fatigue calculations end. And from this point on, stable propagation is where fracture mechanics propagation calculations kick in. And the last stage here is unstable propagation. That means things will, the crack will grow unstable in an unstable manner, and it will just fracture. And so we don't model this last stage here. This is similar to a creep curve where we don't model the last stage of creep, or we don't model the last stage of unstable crack propagation. So, this crack propagation, the simulation content here is where, for example, here, I can do an animation of this, there's a certain crack that's right in the center of a part. And what is our part? Our part is really it's really a demo part that we use in our regular ANSYS training class. We took this part and put a crack right over here, and that's what we are seeing here. We are seeing the propagation, the crack propagation, and of that crack that started initially at the bottom of this part here. So, you know, what I'd like to talk about is how do we set up these cracks, and the simulation context here is, you know, this is what that animation is really happening right here in this stable propagation region. So cracks initiate from an imperfection. They can initiate from an already existing crack, and they can initiate from a damaged area. And so as an engineer, we have to do a failure analysis to see what's going to happen with this crack. And a failure analysis, it has to include a stress analysis and a failure criterion. And this is where ANSYS comes in. You know, this is where we do the stress analysis, and then we also apply the failure criterion in ANSYS. So like in this problem here, you know, one thing we are going to see is, you know, we start out with a geometry, we specify materials, we put in a crack, a semi-elliptical crack in this case, and then we do crack growth calculations over here in Workbench. And so this part is the stress analysis part, and over here at the bottom in post-processing is where we have to do the failure criteria. We have to specify a failure criterion, giving a stress analysis over here. We have to do the failure criterion and determine how this crack is going to grow. So these are really there are a lot of nice features in 19.2. If you have not upgraded to 19.2, this is time to think about it, especially if you're in this area here in fracture mechanics. These type of crack simulations used to take us literally weeks. I hate to say it, but it used to take us weeks a few years ago. But today, this simple simulation that shows how the crack grows, it can be done within hours. And I'm talking about like really couple hours. That's how easy it has become to do crack propagation simulations. And so a failure analysis must include a stress analysis and a failure criterion. And so in the history, as to how fracture mechanics was established, really back in 1921, Griffith came up, he found that the strength of the, he tested a lot of glass panels, and he found out that the glass depended on the size of the crack. And he found out that the global stress, not the local stress, S here represents the stress, nominal stress. The nominal stress in the panel times the square root of the crack length is really a constant. And this he found back in, he established this back in 1920s. And so this was a significant finding, because this is really the basis of fracture mechanics, is this nominal stress times the square root of the crack length, the initial crack length, is really a constant. So this was a significant finding back in 1920s, but it was not really put to use until 1950s, until 1960s. What happened in 1950s and 60s is right after the war, there were a lot of developments in space, in aerospace, as well as in aeronautical engineering and aerospace engineering. So back then, some of you may already know this Comet airplanes, for example. You're getting off the topic here, but let me show you. Comet airplanes here for those of you who already know this. There is let me find a bigger picture of these Comet airplanes. These Comet airplanes, they were built back in 1950s, and they started really falling off the sky. And so it was a beautiful airplane, as you can see here. This was a beautiful airplane, and this airplane, somehow I can't seem to get a bigger picture of this. So this beautiful airplane was the first passenger airplane that started flying at 35,000 feet. And to do that, the cabin had to be pressurized. But this airplane started, there were 3 aircraft that were launched in the ocean. And it turns out that, there were cracks propagating from the square windows. And that's when there was heavy emphasis on fracture mechanics calculations, how the cracks propagate, and then engineers started, especially in 1960s, they started investigating this at nominal stress times square root of A being a constant. And then back in 1959, Williams developed the solution of the crack tip stress field. This is a straightforward hand calculation that he developed and in our fracture mechanics class, we actually go through and we don't, we show you the steps that's taken to solve this problem. How can you obtain the stress field ahead of a crack tip? Like we said, at the crack tip, the stress is singular. So we can now really calculate the stress right at the crack tip. So we are looking at stresses at an infinitesimal length away from the crack tip. And if we look at think of it like a small finite element model here, what's the stress state on this finite element model? So Williams, back in 1959, he came up with a closed form solution, and these constants, K1, K2, these are the stress intensity factors that define the strength of singularity at the crack tip. And these stress intensity factors are functions of the crack geometry, how the crack is aligned with respect to the rest of the geometry and also loading. So basically K1 and K2 determine how much it hurts at the crack tip. And this is under mode 1, this is under shear mode. And they also are basically covering an infinite stress, and they're actually bringing that down to something that can be identified. So anyway, but this is a closed form solution. And as you see, this closed form solution is given as a function of theta, theta being the angle ahead of the crack tip. If you set theta to 0, which means if you bring this down to right ahead of the crack tip, then you get K1 is equal to sigma times 2 pi r, and also K2 is tau xy. This is the shear stress times 2 pi r. And as you see here, it's a function of the radius, how far you're away from the crack tip. So as you can see from this picture, from this formulation, K1 being equal to sigma times 2 pi r, this is very similar to Griffith's finding stress times square root of A being a constant. So that's how it developed, and it's also important to distinguish the difference between K1 and K sub 1c. K1 is the stress intensity factor at any moment in time, and we have to calculate K1. And ANSYS, by the way, ANSYS does calculate stress intensity factors. So under fracture tool, if you click on stress intensity factors, you can get K1, you can get K2, you can get K3. You can get these values. Just ANSYS, as part of the stress analysis in the post-processing, it will give you these values. It will plot them out, and you can see the values here, and it's also plotted here. In this case, it's 3 KSI squared of inch. And you can see the funny units there. It's PSI times inch squared of an inch. These are the units of stress intensity factor, and rightfully so, because of this one. Stress is PSI, and square root of distance is square root of an inch. So PSI times square root of an inch. Those are the typical units, and that's how also ANSYS outputs them. So ANSYS outputs, K1, K2, K3. Then our job as an engineer is really compare these stress intensity factors that are listed here and plotted here. We compare them to the K sub 1C, because K sub 1C is a material property. K sub 1C is going to determine if there is imminent failure or not. So in this case here, we compare, we are getting about 3 KSI square root of inch for stress intensity factor, and K sub 1C for these type of materials is of the order of, say, 25 KSI square root of an inch. And what that means is there's not going to be an imminent fracture. If there's not going to be an imminent fracture, then what do we do? Then we go back to these curves here, and we go back and we compare what we are seeing to the threshold value. So the threshold value is, say, of the order of 2 KSI square root of an inch. That's typically a good number for threshold value, 2 KSI square root of an inch. And from ANSYS, then I look at this, I say, okay, my stress intensity factor is about 3 KSI square root of an inch. Then that means I am on this side over here, and that means I'm going to have crack propagation. And if I'm going to have crack propagation, that's when I start planning for crack growth simulations in ANSYS. So that's where I can go in and do a crack growth simulation, and that's why we were seeing these animations here, because the crack will propagate under these conditions. There is no imminent fracture. What do we mean by imminent fracture? By imminent fracture, if the stress intensity factor was above K sub 1C, then this panel would just break apart just like that. But since K sub 1C is less, the stress intensity factor is less than the K sub 1C, then there's going to be crack propagation. And then that means we can do crack propagation simulation and see how it propagates. So we get into a lot of more details in the class, but here's a very simple hand calculation. Some of this you can do by hand calculation. So find stress to fracture an aluminum panel with an edge crack. Let's say you have an edge crack, and the edge crack is, let's say, I'm just making up numbers, 0.1 inches, right? And it's an infinite width for panel, and K sub 1C for this material is 26 KSI square root of an inch. So through hand calculations, we know that for an infinite width for panel, if you have an edge crack, the solution of K sub 1 is really, K sub 1 is equal to 1.12 times nominal stress times square root of pi A, where A is the initial crack length. So 1.12, you may say, where did this number come from? 1.12 is a geometry factor. Remember we said, stress intensity factor is a function of geometry, and it's also a function of loading. This, for the case of an infinite panel with an edge crack, then 1.12 is the right solution or is the right geometry factor. So knowing this formula, K sub 1 is equal to 1.12 sigma times pi a, what do we know? And what are we being asked as an engineer? Our customer is saying, find the stress to fracture an aluminum panel with an edge crack. So in this formula here, I know the A value, which is the crack length value, and I know the critical stress intensity factor. So at the onset of fracture, when there's going to be imminent fracture, I can take this formula and I can start putting C values, the critical values for everything. So K1 becomes K sub 1C, sigma becomes sigma sub C, which means we are trying to find the stress to fracture, and A becomes A sub C. And if I solve for stress from here, it's K sub 1C divided by this number here, that comes out to be 41 KSI. That means if the nominal stress in the panel reaches 41 KSI, this panel with a 0.1 inch crack is going to have imminent fracture. And so through formulas like this, closed form formulas, this is how we also verify and also in some cases through experimental observations, we validate ANSYS models. So in ANSYS portfolio, you can calculate stress intensity factors, you can calculate J integral. How do you calculate J integral? If you do a right mouse click on solution, under fracture tool over here, you can say, okay, show me the J integral value. Show me VCCT results, material force results, T stress, C star integral, equivalent stress factor range. Well, and in our fracture mechanics class, we also go through all of these here. What's J integral? What's material force? What is T stress? What is C star integral? And I can let me take a brief moment to explain C star integral. That's where for creep formulations, say if you're working with aluminum and titanium and you have creep, and so for creep crack growth, you can use C star integral. So in the ANSYS post processor, you can do all of these. Material force. So in ANSYS fracture mechanics with 19.2, you can do these fracture parameter evaluations. And again, the reason we do that is because we want to compare what the stress intensity factor or J integral values are compared to the critical values, so that we can make an immediate judgment call as an engineer if there will be immediate fracture or not. And also crack growth tools. How can we do crack growth simulations? And as you see here in ANSYS, yes, we can do crack growth simulations, just like what we are seeing here. And so the crack growth simulations, crack growth tools, there's CZM method, there's VCCT method, and XFAM method. Those are all available. And we're going through the details of what these are in our fracture mechanics class. And also in ANSYS mechanical, we can insert a semi-elliptical crack very easily. We can insert an arbitrary crack very easily. Then we can do fracture parameter evaluations. We can do debonding and delamination analysis. Debonding and delamination, there's slight differences between debonding and delamination. And we also talk about what's the difference between debonding and delamination. In ANSYS Workbench, you can do these simulations as well. And if nothing fits what you want to do here, then you can use the ANSYS customization toolkit. That's the ACT in ANSYS to develop your own fracture mechanics capability. So, for example, for those of you in the bearing industry, if you'd like to couple bearing programs with ANSYS, then you may want to look into this ANSYS customization toolkit as well. Okay, so I just want to go back, and we have a few minutes left. I'd like to take you through how to set up this problem here. In this case here, we have a simple geometry. This is our geometry over here. This is our geometry, and we do the very first thing you may want to do before you put any crack is you need to specify a crack coordinate system. The crack coordinate system is placed at the location where the crack is. And as you see here, the crack coordinate system is specified right at this location here. And this region is, it turns out this region is a location where there's tensile stresses. So when you specify a crack coordinate system, you have to put the crack coordinate system right at the center of the crack. The x-axis, very important, the x-axis of this local coordinate system has to be going into the material. So x has to be going in, and y-axis has to be perpendicular to the crack plane. So, and then when you specify a crack, you insert a crack. These are the parameters that you specify in the lower left-hand corner. The first thing is you specify the crack coordinate system. So you have to let ANSYS know where you're going to place that crack, and that's determined really by this coordinate system here. So then you can specify a major radius or a minor radius. In this case, we are doing a semi-elliptical crack. For semi-elliptical crack, then you can specify a major radius, a minor radius, and then you can specify largest contour radius. What is the contour radius? It really specifies the contour radius right at the crack front. So as you see here from this model, the solid model does not have to have a crack. You actually start out with a solid model that does not have a crack. For example, here I'm looking at this. My solid model does not have a crack. That's really great news. That means I can specify a crack in my mesh. I can embed it in my mesh. But the way to do that is really by specifying a coordinate system at the location, and then specifying these parameters over here, the major radius, the minor radius. In my case, it's a semicircular crack. As you know, if the major radius is equal to minor radius, that becomes a semicircular crack. So I put a surface crack, semicircular crack, right at that location, and that's really the most important thing, is specifying a crack coordinate system. So let me show that to you. This is just starting from very scratch. So the first thing you may want to do is go in here and insert a coordinate system. And right away it says, okay, where would you like to place the coordinate system? I say, I want to do it with global coordinates. And what we are seeing here is the global Cartesian coordinate system here. Now, what I'd like to do is somewhere here, I'd like to put a crack. So to put a crack right on that surface, the very important point here, I'm going to go over here and I'm going to select at the very top, I don't know if you can see it, at the very top where it says, there's an option here, hit point coordinate. Hit point coordinate, that's really a nice feature in ANSYS Workbench. So after I click on it, I can move my cursor into the window and I can actually see the XYZ coordinates or where my cursor is. And if I click on this geometry here, you will see that there's it's marked, that location is marked. Then I move my cursor to the lower left-hand corner and I click on apply. So as soon as I click on apply, it put a local coordinate system right over here. But in this local coordinate system, the x-axis is going not into the material. So how can I change that? That's very simple. I need to rotate this around the y-axis. So what do? I go up here. It says rotate y. I click on rotate y, and I just type in -90 degrees. And now right away, I put a local coordinate system here. So that's my local coordinate system here, and you can rename this. You can give it any name you like, crack coordinate system, for example. And then if you click on model, then you have to insert a fracture. You insert a fracture that adds in a fracture into the model stage. Then you do a right mouse click on that and you say, you can insert an arbitrary crack, semi-elliptical crack, pre-mesh crack. In ANSYS APDL, you can mesh a crack and then bring it into Workbench. Or if you are doing interface delamination or contact debonding, you can do that as well. Let me show you the semi-elliptical crack option. And as soon as I click on semi-elliptical in the lower left-hand corner, it says, okay, you need to tell me how you do this. So I want this crack in this part over here, and I would like to use the crack coordinate system, and I'm going to use 50 thousandths of an inch for the major radius, 50 thousandths of an inch for the minor radius, and 25 thousandths of an inch. And right away, by just putting those three numbers, ANSYS implemented a crack over here. Now, please note that when I mesh this, generate mesh, see, it generated a mesh that's really a very coarse mesh, right? And in Workbench 19.2, you can go under resolution and you can say, well, I'd like to have slightly finer mesh over here, and it just comes back and it says, okay, I put a finer mesh and I also mesh the crack for you, right? It already meshed the crack. And again, I don't have a crack in my solid model. All I did was bring in the semi-elliptical crack, and it was able to put it in here. So I'm going to switch back to this. So as you see here, after I do the simulation, the crack, ANSYS calculates the stress intensity factors. It calculates number of cycles that this crack will propagate. And it says that the number of cycles over here is 539. So it's going to propagate 539 cycles before it actually fails. And so ANSYS gives you all these information over here. So in the interest of time, I'm going to stop here, but this is really a deep topic. This is, fracture mechanics. That's why we have a 2-day class where we will teach you how to do these crack propagation problems, and so that you can see how you can implement these crack growth tools and do these type of simulations, and also this CZM cohesive zone model, how you can do these type of simulations as well. So these are more examples of how you can do these fracture mechanics problems. And here's another example. It's basically, as you can see here, the crack growth is really calculated by, when the critical fracture energy is reached, and ANSYS can calculate a path that's not in mode 1 only, and ANSYS will calculate that path that can go in a nonlinear fashion, just like that example that we see there. So as you see, it's not a planar crack growth, but it goes and it starts curving up. So we will show you, there's a fracture analysis guide in 19.2. I mean, it existed before, but it has been enhanced in 19.2. There's a fracture analysis guide. There's a lot more information that you can get. And if you're interested, you can attend our fracture mechanics class to get more in-depth information. And again, that's set for November 8 and 9 in our Durham office. So I'm going to stop here, and I'm going to stop here and turn it over to see if there are any questions. So you can type them in under the chat window. Also, please contact Boz if you're interested in these other webinars. We have the contact nonlinearities. Oops, that's the wrong date. It's actually on Friday next week. And also, if you're also interested in the fracture mechanics class, please contact him. So info@mallett.com. That's the address. So email address. Okay. So yeah, if there are any questions, please feel free to ask. But if there are no questions, thank you for your time, and please let us know if you'd like a copy of this recording. It's being recorded, and so we look forward to seeing you in our future webinars or in our future classes. Any questions, please feel free to contact Boz or our team in these offices, in Durham office, and we also have an office in Maryland. So we'll look forward to seeing you in our future classes and in our future webinars. Thank you.
Well, yeah, thanks everyone for attending. Everyone have a good day.
Thank you, Bob.
Thanks, Bob.
Hi, Boz, you may want to stop the recording.